Okay, we'll start our next session. Up next, we have Innokentii Sennovskii from Aztec Labs presenting Zero Knowledge, Full Coverage, a Fuzzing Paradox. Expect an in-depth discussion on how coverage-guided fuzzing meets AI-assisted automation and the trade-offs between volume and understanding in vulnerability discovery. Please welcome Innokentii on the stage.
Yeah. Hi, my name is Innokentii Sennovskii. I'm going to talk about how to fuzz not such a traditional program on test, specifically zero-knowledge circuits. About me, I'm the head of security at Aztec Labs. My main focus is making every part of zero-knowledge protocols secure. I'm also organizer of the CTF Zone competition, and I teach attacks on applied cryptography systems at the university. So today I'm going to talk about what zero-knowledge proofs are, talk more about specifically zero-knowledge circuits, what kind of bugs there are in zero-knowledge circuits, how fuzzing works in general, and what's the difference and why it's so difficult to create fuzzing harnesses and to implement fuzzing in zero-knowledge circuits. So first, there are two things I have to say. All the views here are my own, and I gloss over some cryptography specifics. I simplify them just because if I were to dive very deep into them, 45 minutes would definitely not be enough. So first, what is a zero-knowledge proof? The basic idea is we have two entities, a prover and a verifier, and the prover is trying to prove something to the verifier without revealing any additional information about the statement. So let's say a very simple example, and an intuitive one. Let's say everyone knows what Sudoku is. For those who don't, it's a very simple game where you have a field of 81 numbers, so it's 9 by 9, and each row, each column, and each subsquare of 9 elements has to have all elements from 1 to 9. And let's say we have a prover who wants to prove that they know a solution to the Sudoku puzzle without revealing anything about the solution to the verifier. So they want to know, I can solve this, I know the solution, the verifier doesn't. So how would we do this? Well, the first thing is you'd have to buy 27 card decks. The idea is you just need to represent the numbers in the Sudoku with cards. Out of those 27 card decks, you create 81 free card decks, where each free card deck has the same card. So for example, if we want to symbolize 1, it would be the ace, repeated 3 times. If you want to symbolize 2, it would be the 2 of hearts, repeated 3 times. So you're just using them so that you can place them securely on your field. What happens next is the prover takes each of the stacks representing a number that is already on the Sudoku field, and it places a similar stack of 3 cards face up onto the field. So at this point, the verifier knows that, these cards are in the same place as in the original Sudoku description. Next, the prover takes the other card stacks and places them face down on the field. So at this point, all of those card decks are on the field. Each of them has 3 of the same cards. So for example, in the top left corner, there could be 3 of 1s or 3 of 9s. It's going to be the same card. The prover does this in full view of the verifier. Then the prover turns the previously facing up cards down so that everything is now hidden. So we have a full field that is hidden, but we know that the cards on the specific spots that were defined initially stayed the same as in the initial setup. What happens next is the prover takes 1 card from the top row, from each element of the top row. They start shuffling those cards and they give the shuffled cards to the verifier. The verifier then takes those cards and checks that those cards contain all the elements from ace to 9. So they have the representation of all the values from 1 to 9. So at this point, the verifier checked that the top row indeed had all the elements. We continue with the same principle by going through each of the rows. So each time the prover takes cards from the row, shuffles them, gives them to the verifier checks, yes, it is indeed all the cards from ace to 9. We continue with all the rows. We then switch to columns, and then we go through all the individual squares, repeating the same shuffle, give to verifier, shuffle, give to verifier. And in the end, what happens is the verifier checked that each row had all the cards from 1 to 9. Each column had all the cards from 1 to 9. And each of the predefined, each of the squares has all the cards from 1 to 9. We also know by the way we constructed it that each of the initial cells that were defined to be particular elements had those specific elements. But at the same time, the verifier knows nothing beyond that. So that's a simple toy example of how zero-knowledge proofs work. The verifier has learned that the prover knows the solution to the Sudoku, but it hasn't learned anything at all. To look more into how this works in cryptography, there's a simple primitive that we have to talk about, the discrete logarithm. So there is a property of secure prime numbers that if they're large enough, then one operation is very easy. If you exponentiate an element into some random value modular this secure prime, then you get an element, and it's very easy to perform this operation. But if you're given the elements x and y, and you have to find the logarithm, but if you're given the generator and the element y, then finding the logarithm is extremely hard. And by extremely hard, it means that, for example, if we pick a large prime number, which is 4096 bits, it's basically impossible with the current computational resources in the world. So from this, we can construct an interesting primitive. So we want to prove that we know the solution to this element, so then we know the initial exponent to the verifier. How do we do this? We pick another random number and exponentiate this with the same generator. We send it to the verifier. The verifier gives us a random challenge, which is in this field, and we compute a combination of our randomness that we've generated initially and our secret, which is x multiplied by the challenge given by the verifier. The verifier can then check that the computed value that we sent, the value s, is constructed in the same way as the initial randomness that we committed to, and the element which was exponentiated to the secret exponent x, once again exponentiated to the challenge. So they can check this property independently without us actually revealing the secret. Why do we say that this is zero knowledge? Well, there is a very simple trick that cryptographers use, which is to say, let's say we can predict the challenge that the verifier sends us back. If we can do that initially, we can construct such an initial random value r that will always satisfy the condition that the verifier imposes on us. So what do? Instead of computing, instead of sampling a random k and then sending g to the power of k, we send g to the power of k multiplied by the y element to the power of minus predictable challenge. Then we get a predictable challenge, then we send the s, which is equal to our randomness, and the same check that worked in the past for the actual protocol works once again, but this time we managed to trick the verifier. So we told them that they think that we know the x. Since we didn't actually know the x, but we managed to prove this to the verifier by making the challenge predictable, it means that there was no knowledge in the protocol at all. And since we can't extract any information from it, that means that this protocol is zero knowledge. You've actually probably used this protocol unintentionally, because if you substitute this verifier challenge being created by the actual verifier with a hash, then this becomes a Schnorr signature, which are used everywhere nowadays. So how are zero-knowledge proofs actually used today? There are a ton of modern users. So one, which is pretty widespread, is private payments on the blockchain. The other extremely useful one are identity checks. So one of the applications that are available today is ZK Passport. There are other similar applications where you can scan your passport, for example, the NFC chip, and then you create a zero-knowledge proof that you are the owner of a passport from a specific country, and you're, for example, of age, so you're more than 18 years old, without revealing any other information to the other party. So that will be the only information that's given. You can also use it to prove email receipt. So, for example, you can show that a particular company has messaged you. You can reveal only part of the email and check that everything else is in line with some procedures, but without revealing any other information. And one of the most tough and one of the hardest things to actually prove, but which is possible today, is that you can even prove the results of binary execution. So, for example, if you have a RISC-V binary, you can show that if you give it a particular input, the result of the execution of that binary on that input is going to be the following. So, yeah, there are tons of other users too. But for all of these complex users, you have to use ZK circuits. So those are primitives which are a bit harder than the signature that I showed before. So what are ZK circuits? Basically, you can think about them as programs in the ZK world. So the way the prover and verifier would work if we're talking about a ZK circuit is initially they have some sort of program description, and you can think about it as a regular standard program. We then convert that program description into a circuit description, which is more malleable and more friendly towards the cryptographic primitives which are used in ZK proofs. And then the prover will use that circuit to create a trace, which is some intermediate variables, and in the end create a proof with a backend, with a proven backend. The verifier will convert the same circuit description to a verification key, which you can think about similar to a public key in regular cryptographic systems. And when the prover sends the proof to the verifier uses that verification key and checks the proof against it, and basically receives a Boolean yes or no, like is the proof correct or not. How do ZK circuits look concretely? So let's say we have a Fibonacci program. This is simplified. I know there might be some errors, but this is just to fit in onto the screen. So we have a simple Fibonacci program with where we're trying to figure out the value at a particular step. So the implementation would be fairly similar in a language called Noir because it's created to be Rust-like. So, but there are some limits. So you can instantly see that there are several properties that we have to specify, which are different from Rust program. So one is visibility. In the zero-knowledge proof, you have to show which values have to be public. So these are the values that you are proving to the verifier. So, for example, some input can be public, and the results of the computation also have to be public. Otherwise, there's no point. Then the basic type of ZK circuits is not usually, at least U8 or U32, the base type is a field element. And usually this is a large field, although for some proving systems it can be a 32-bit prime number. But for example, the one that Noir uses is a 254-bit prime number. And everything else is actually defined on top of them. So they're the most basic type in the system. And one more important thing is that we have finite execution length. So ZK circuits are not Turing complete. We always have a limited trace. So you can think about it as the number of CPU instructions that you can execute is always limited up to a certain point. So here we, for example, say that there are only 3 steps. We can increase that number technically, but you'll see why I haven't in the next pages. So That previous representation is then compiled into an algebraic circuit intermediate representation. And the point is that we are creating a list of formulas that work well with the cryptographic backends. Let's dive into what actually the algebraic circuit intermediate representation is. So you see a lot of asserts in the code, and those asserts specify the constraints on the logic, on the intermediate variables, on the intermediate states within the system. So like Sudoku before, you can think about them as defining the rules, but without actually enforcing a particular transition between the variables. So unlike CPU, unlike execution on the CPU, where you have a previous state and then you have a next state, and the previous state completely defines the next, what you have here is the state of all of the whole circuit, and any list of variable values that will satisfy these equations will can actually be proven. Most of the time, though, you can compute the following variables from the previous ones. Then there are black box opcodes. So the difference between the assets and the black box opcodes is that black box opcodes use the underlying proving system defined functionality in addition to like standardized functionality. And here, for example, we're saying that the value only can be from 0 to 2 to the power of 32 minus 1 value. Then there are Brillig calls, which are calls to unconstrained functionality. The idea is that a lot of the time it is very easy to prove a property about the value. So, for example, you can say that b squared is equal to a, but you initially have the a value. And the problem is, in the circuit, using the finite field logic, it is extremely hard to compute the square root of an element. But it is extremely easy to check this property. So what you do is you call some other unconstrained functions, and you just put this value in the circuit later to constrain it against the properties that you want. So let's see into how specifically the Rust-like Noir code translates into these constraints. So the first is, yeah, we have specializations for the parameters. So the second parameter is going to be private. There will be public arguments A and target step, and the value is going to be specified as public too. What you can see is that since they specify the target step to be U32 integer, it's going to be range constrained immediately. So we are showing that this is a value from 0 to 2 to the power of 32 minus 1. Then at step 1, what's happening is you can see that we're performing a Brillig call. This Brillig call is basically computing an inverse value. And the point is that that value is needed to compute the value W5, which is going to be a Boolean. So we're computing a value that is either 0 or 1, and it will always be constrained to be 0 or 1. And 1 when the input for the target step is specifically 1. We also then compute the value W9 to be either the initial value, W0, which was inputted, or the value W5. So you can see that if, or the value W1. So this is basically a conditional select that you see in the assert W9 equal minus W0 multiplied by W5 plus, etc. When we go into the next steps, they also get unrolled, and what's happening is we're performing once again the similar logic. So we are creating a Boolean value that is then constrained to be dependent on the W2 minus 2. So if it's if our target step is set to 2, then the W7 value becomes 1, and then that W7 value is used to actually assign the W13 value to ensure that either we're using a previous value that is transferred, or we're computing a new value. And if you look again at the next step for the I equals 3, then you'll see that this logic is repeated once again. So we are creating a Boolean value, and we are conditionally assigning the result to be a linear combination of the previous value. Since this is Fibonacci, the compiler automatically optimizes it out to basically be a certain multiple of the initial arguments. So that's the way circuits are structured in the intermediate representation. So what kind of zero-knowledge bugs are there in general? To understand it first, I need to establish some terminology. So asserts and black box functions that I talked about are called constraints. Constraints enforce some rules about the system. Brilliant calls don't do anything to enforce rules about the system. You can think about the prover as being able to change any values in the Brilliant calls. They can return anything from there as long as they fit the other asserts. And we also have this term called the witness, which is a specific assignment of all the intermediate variables that fits the constraints. So a witness is anything that fits all of the equations that were specified in all the black box functions. So there is an important ZK circuit property, which is that you can, as long as you have a witness that fits all of the equations, you can prove it. It doesn't matter what the intention of the programmer was. Like, if it satisfies all of the constraints, then it is going to provide a valid proof. And so, because of that, there are soundness bugs, where, let's say, a Ron Sudoku solution is accepted. Usually, they come from the fact that necessary constraints are missing. There are some logic issues, or somebody is using unconstrained functions in place of actual constraints. So a very simple example would be, this is code that I've seen where a person was trying to save some gates, so some assertions, because assertions are costly. And when you increase assertions, you're basically increasing prove time, and it takes longer for the system to work. So in this case, a person was trying to implement a U128 primitive based on two U64s, and instead of checking each individual field to be equal, they basically took a difference of individual fields, multiplied them together, and checked that to be 0. The obvious problem is that even if one of them is equal, then it immediately returns true on the Ron equality. Then there are completeness bugs, which are fairly widespread. This is when the person has implemented the circuit incorrectly, or for example, some primitive was implemented incorrectly, and it doesn't allow you to prove something that is considered correct. So let's say you are translating some program into this domain-specific language, and you forgot to specify an edge case, then a user would not be able to prove something that should actually be proven. So a simple example is, let's say you wanted to prove that the sum of values is equal to 0 modulo 2 to the power 256, so regular U8, but you forgot that in Rust-like languages, this would cause an overflow, so you needed to use a wrap and add. So this would become then be only possible with the solution 0,0, and that would limit the amount of solutions. And then there are zero-knowledge bugs where we're basically leaking some information. I'm not going to talk about them after this because it is hard to find them with fuzzing in general and with such automated techniques. But the basic idea usually is something is wrong at the proving backend, or somebody set the public modifier to the wrong inputs. So the way traditionally ZK circuit bug is being detected is with unit testing, end-to-end testing. There's a lot of formal verification being used nowadays, and there's a lot of auditing. And auditing, I think, is one of the most widespread ways that most teams perform circuit bug detection, but unfortunately there are several issues with this. So one unit testing is obviously too much dependent on the developer. It doesn't test component interaction, and it's hard to test everything. The end-to-end testing is also quite limited because it follows predetermined paths and edge cases. Formal verification is very limited if the programs are large. If you are trying to compose several primitives at once, you immediately run into the block, and even the best formal verification systems, such as CVC5, can't really handle large circuits. And audits are very human-dependent, non-scalable, and they cost a ton. Some teams take as much as 25,000 per researcher per week for an audit. So what can we do? Well, obviously there's fuzzing, and I know most people here know about fuzzing, so I'll be very quick. So what's black box fuzzing? You generate some randomness, you put it into the program, and you look out if there are bugs. The problem with the black box approach is that the probability of finding anything useful and deep is quite low, because let's say you have a 4-byte string, just creating a correct 4-byte string has a very low probability. So the way we solve this is with gray box fuzzing, where we introduce the concept of coverage. We see which branches were taken within the program, and if we see some new functionality, we write the input that caused that new functionality to be triggered into the corpus, where we then take the values from, mutate those values, run the execution again, and this allows us to progress through the program, changing the probability space, and then finally find the triggering test case and finding some bugs. The problems with circuits is that there's no branching. So if you see with the algebraic circuit intermediate representation, we just have a bunch of asserts, we have some Brillig calls, but that's it. You can't really see the branch, and so that means that you can't easily use traditional coverage. So what can we do? Well, the first thing is Noir supports so-called unconstrained functions. The idea is, like I said, you want to compute something outside of the circuit and then put it back. And there should be a convenient way for a developer to write those kind of subprograms, so we have unconstrained functions. And unconstrained functions use what's called a Brillig VM. It is a virtual machine that uses field, U8, U16, and up to U128 types. It has contiguous memory, and what's useful is it has branching. And so what we can do is we can compile the same ZK circuit to also be compiled to the Brillig variant. So we have a traditional circuit variant, and we now have a Brillig variant which has the code which is executed in the VM, has branching. So now we can take the coverage from this twin and use it in the fuzzing process. In this particular case, so the coverage that we're taking is obviously the branching, and I also implemented the value proximity mechanism. So now we are using the Brillig execution for the analysis, but we are also submitting the same test case into the Acer circuit to check if there are actual bugs. So yeah, if we get a regular fuzzing harness, traditional one, this is what it looks like. Yeah, and we found the input string. The thing we run in next is the computation complexity. So here you see a simple program where we're just shifting a value by a number of bits, which is taken from another value. But you can see that the Acer version, which is the second one, is much longer than the third version, which is the VM one. There are several issues with this. One, the Acer computation uses finite field logic. It means that you are performing a 254-bit computation per each value. It is quite computation heavy. There are no quick paths. You can't just do if-else if you've entered a different if you want to get out of the program early, which means that you're computing all of this trace all the time. So all of this significantly slows down fuzzing. it is very hard for us to explore a lot of states quickly. So what do? We try to balance the execution between Brillic and Acer. So what we want is to have as many different inputs to go into Acer, but the problem is if we try to fuzz by sending test cases to Acer and Brillic all the time, we're going to get slowed down. We won't be able to explore as many features as possible. So we basically split the time in half between the Acer execution and the Brillic execution in the VM. Because of this, Brillic is getting executed like 10 times more often than Acer, but we explore more of the target program. So we are able to figure out more interesting stuff about the final program. Unfortunately, we are still running into a lot of issues because circuit writers don't like branching in general. So while ifs are available to them, a lot of them will just use intermediate Boolean values to guide some logic, which means that even if we compile this into the Brillic VM code, we don't really explore the functionality a lot of the time. So for example, this kind of code, obviously, even in the VM, will just be a single trace without any branching, so we would not be able to find the results. So what can we do? Basically, when we are solving the Acer, we get the witness value in the end. And we think that when we're doing conditional selects, all the values are 0 or 1. We also use similar to conditional select logic in other places where the values once again are becoming only 0, 1, so they have only Boolean values. So what we do is we parse the final witness, if we manage to get to the end, for all of those values, and we try to figure out if we've found a new value, which we haven't seen, out of those Booleans. As a result, it allows us to progress through even programs without actual branching. So we just explore all of the switches and all of the different states within the program. And so even a target like the previous one can then be easily fuzzed by just looking at all the intermediate values of the variables. So yeah. Unfortunately, there is a bit of a problem. So the following program, we will also, we can easily find some issues within the circuit, but not always those are the issues that we're trying to find. So the idea is we want the circuit to satisfy various conditions, but let's say we're submitting values of A and B which don't satisfy some intermediate conditions, like they're causing an underflow, and we do want to catch that underflow. It is an intended underflow, but we want to check that all the other more important properties are actually observed. We have to have some sort of oracle, basically, that the specific condition that we're looking for is not getting satisfied. So basically, what we do is we also introduced a mechanism where we're targeting specific conditions and we are ignoring all the other failure conditions. This allows to check that invariants are implemented correctly, that the code base adheres to particular invariants. So, yeah. So yeah, here we can see that the particular assertion that we were interested in has been broken. Some other features that have been implemented specifically for Noir are multi-threading. There are time and count limits. There are fast tests for CI integrations. There are also specialized mutations for each basic type and for structures. So for example, you can define a structure as an input to your program. It will automatically parse it and be able to randomly pick out the values and structurally mutate it. There's state-space splicing, and there's an autodict which takes values from the finalized Brilliant representation and from the finalized Acer representation. And one of the most important features that have been implemented is a Fuzzing Oracle integration. So it's very easy to create a JSON RPC server that actually checks that whether your program is supposed to be failing right now, especially if you're implementing some sort of cryptographic primitive. You can, for example, fuzz against an OpenSSL library to check that this is implemented correctly. And so here, for example, I have an example of fuzzing on 64 threads at the same time, where I was fuzzing a JSON library, specifically whether the passing of a particular string was done correctly, and if you could create an invalid JSON object that was still passed by the library, and it was using the Python JSON parser as an oracle. So, yeah, that was basically all I wanted to talk about today. Thank you very much. If you want to ask me anything about zero-knowledge proofs or circuits, there's huge scope for security work here. Yeah, please talk to me offline or ask any questions. Thank you.
Thank you, Innokentii. That was a sharp and thoughtful presentation. So do you have any questions?
I think it wasn't very clear what the role of the Brilliant execution plays in the fuzzer. Could you reiterate over that?
Yeah, so the idea is you have a program which is hard to observe, right? So think about it. You have not a program, a platform that is hard to observe. You can't really extract coverage information from there in the regular way because it doesn't have branching, it doesn't have the stuff that we usually look for when we're trying to extract coverage information. So what you do is you compile absolutely the same code to a different platform.
Okay, I got it. So my question is, essentially, from my understanding, what you're trying to do is you're doing differential testing between the Brilliant ISA and the ZK circuitry, am I correct?
Not exactly, because usually differential testing is you have two different implementations and you are checking if there's a discrepancy between them. Here I'm using so I'm testing one implementation and I'm using the second implementation to guide the testing process. So I'm not looking for the bug specifically in the second implementation as much.
Oh, I see.
I'm only using it so that the first one, so that I can explore the first one, so that fuzzing is useful, because otherwise it becomes the black box.
Okay, then my last question is, you mentioned something about instrumenting Boolean values in case the author elides using branching. In that case, why do you not instrument the Boolean values in the Brilliant execution and use these circuits?
So in Brilliant, it's harder because in Acer, because it's a single trace, you basically have always a limited number of values. So think about it as you have a program that always executes the same way, and you can observe the values of all the intermediate values of the registers, right? And then you look for those, and you can switch based on those. Brilliant, at the same time, is a VM, so you would actually have to record all of them. With Acer, you already have a recording of all of them, so you can just take those and analyze them easily. So it's already an unrolled trace. You don't have to do anything extra for it.
I think that checks out. Thank you.
Thank you for the questions.
Thank you, guys, and please give him a huge round of applause.